In this video, I'm going to solve every question from the UKMT Intermediate Maths Challenge from 2023. That's one of the main maths challenges in the UK, usually taken by students aged 13 to 16, but often also taken by younger students as well. And if you're preparing for that challenge, then take a look at my free course, Get Ready for the Intermediate Maths Challenge. In that course, you can practice all of these questions, as well as questions from other papers, and each question has a video hint and a full video solution, so you can have a go at the question, watch the hint if you're stuck, you can really get the best chance of answering it by yourself, you can then see if it's right and watch the video solutions. It's a really great way to prepare for the Intermediate Maths Challenge. And over at that courses website, I've got loads more courses to prepare for maths challenges and school maths as well, so I really hope that you'll take a look over there. But if you'd like to watch the solutions here on YouTube instead, I'll get on with them now. I'll put timestamps below so you can jump to the questions you need, or if you'd like to work through the whole paper with me here, then we'll start at question 1 and you can pause the video at the start of each solution. Which of these numbers is neither a multiple of 3 nor a multiple of 4? This is the first question of the IMC here, and it should be fairly easy. We could just go through and check them individually. Remember, we've also got the divisibility test for multiples of 3, which says if the digit sum is a multiple of 3, then the number is a multiple of 3. So I could immediately see, if I didn't already know, that 21 is a multiple of 3 because 2 plus 1 is 3. So that one is definitely a multiple of 3. 2 plus 8 is 10, so that's not. 3 plus 4 is 7, which is not. 4 plus 5 is 9, so that one's a multiple of 3. And we can also see that 16 is 4 times 4, and that 28 is 7 times 4, so the answer to this question is D, 34. What's the area of this triangle? Slightly trick question perhaps here in question 2 of the Intermediate Maths Challenge. We've got, if we do half base times height and do a half 4 times 5, we'd get 10, but actually that's not the base and the height, right? The way they've drawn this triangle, the base and the perpendicular height would have to be this length and the 4 centimetre length. So I need to work out this one as well before I go on, and we can of course do that with Pythagoras theorem, or noticing perhaps that we've got a 3, 4, 5 triangle, but if this was x, then we'd have x squared plus 4 squared equals 5 squared, so x squared is 25 minus 16, which is 9. X has to be a positive number, so that gives me x equals 3, and so the area of the triangle then is a half base times height. It's actually a half times 3 times 4, which is 6 centimetres squared, and so the answer here is A. To work out question 3 of the IMC here, we've just got to look at the nested brackets in order from inside to outside. So 5 minus 6 would give me minus 1, then I've got to do 3 minus 4 minus minus 1. So 3 minus 4 is minus 1, but then minus minus 1 gives me plus 1, so that's minus 1 plus 1, so this bit here is 0. So actually I've just got to do 1 minus 2 minus 0. Well, 2 minus 0 is just 2, so I've got to do 1 minus 2, and that gives me the final answer here of B, minus 1. Question 4 of the IMC here, we've got 2 diagonals and 2 line segments, each of which connects 2 midpoints of the sides of the square. What fraction of the area of the square is shaded? Bit of a classic maths challenge style question here, the sort of thing that comes up a lot and that I've also put in my online courses a lot. So really adding some extra lines here makes this question quite easy, and there's a bit of an art that you learn to doing these sorts of things, but if you just add some extra lines in here, we can see there's a lot of symmetry in this shape, and actually that this shaded part is exactly just 1/4 of 1/4, or 1/16 of the shape overall. Question 5 of the IMC here is just about calculation. It says we know that 1 plus 2 plus 3 plus 4 is 10. That's irrelevant really to this question, but it says it's also true that 1 cubed plus 2 cubed plus 3 cubed plus 4 cubed is 10 to the n. That's where the real question is. So we've just got to work this out. 1 cubed is 1, 2 cubed is 8, 3 cubed is 27, and 4 cubed is 64. If you add those together, we get 9 plus 27 is 36, plus 64 is 100. You can probably guess the answer from the rough size at this point as well, but 100 of course is 10 squared, and that's the n that we're looking for here then. N is the power here, which is 2. It often helps to consider even simpler cases of these sorts of things. So if I started with a 1 by 1 square and thought about how many horizontal and how many vertical lines there are 2 horizontal lines along the top here, and there are 2 vertical lines on the left and the right here. Now if you go to a 2 by 2 square, then there are now 3 vertical lines, and there are going to be 3 horizontal lines as well. And if we go up to the 3 by 3 one that we can see here, where we've got 8 lines in total, that's because there are 4 down and 4 across. So you can see in general we're going to need 1 more horizontal line and 1 more vertical line than the number in the for the grid. So if it's a 3 by 3 square grid, it's 4 and 4. So if it were an n by n grid, I'm going to need n plus 1 vertical lines and n plus 1 horizontal lines, and so the answer to this question is that we need 2 times n plus 1 lines in total in general. And of course, if you can see that in general to begin with, that's great, but if not, just thinking through a few cases is always a good way to go. Clearly, this question is all about getting the right number of zeros, in particular being careful with 0.015%. So if I took the number 0.015 and turned it into a fraction, that would be 15 over 1,000. Okay, but we want 0.015%, so I need to divide by another 100, so I'm going to end up with 2 more zeros on the bottom here, so I'll have 5 zeros. So actually 0.015% of a number is 15 over 100,000, 15 hundred thousandths of that number. So I need to do 15 100,000ths of 60 million, and 60 million would be 60 with 6 zeros. Now I can do some cancelling, so I've got 5 zeros here, 5 zeros here, and I'm just left with 15 times 600, and so the answer is 9,000. That's B. We've got an equation we want to solve here. The square root of the square root of x is equal to 3, and when we're dealing with equations, we just need to make sure we do the same thing to each side of the equation. So if I square both sides of the equation here, I get the square root of x is equal to 9. Then if I square both sides of the equation again, I'm going to get that x is equal to 81. Another way of doing this would be to say that you know that the square root of x is x to the half, and then I'm raising that to the power of half. So if you know your indices rules very well, you can say, well, that's just x to the quarter, so that's the same as the fourth root of x. So we could have just done this in one step if you spot that, and then just say that x is 3 to the 4, which of course is also equal to 81. Either way, just as good there. Marian's written down these numbers 2, 0, 2 and 3, and there's one more number, and we want to know what the median is. More information required here is an option, but that's not going to be the answer, and you should only ever go for that option if you can really come up with 2 different possibilities. So the reason there aren't 2 different possibilities here is if we think about putting these numbers in order, 0, 2, 2 and 3, right, because the median is the middle value once the numbers are in order. And just think about where all the possibilities are for the final number, right? So it could be something smaller than 0, like -1, then the median would be 2. It could be something in between 0 and 2, but 2 is still the middle number here. It could be another 2, in which case 2 is the middle number. It could be something between 2 and 3, in which case 2 is still the middle number, or it could be something bigger than 3, and then 2 is still the middle number. So in all cases here, the median is 2, and so the answer is B, 2. Let's fill in this cross number. We've got a power of 5, a power of 6, and a power of 4 to fill in. We'll just do them in order here, 1 across a power of 5. It's got to be 4 digits, right? So 5 to the 1 is 5, 5 squared is 25, 5 cubed is 125, 5 to the 4 is 625, and 5 to the 5 is 3,125. If I go to 5 to the 6, that's going to be 15,000 or something. That'll be too big. So this answer here must be 3125. For 1 down, a power of 6, well, 6 to the 1 is 6, 6 squared is 36, and that's as far as we need to go. 6 cubed would have 3 digits, so this one must be 36. And then for 2 across, we've got a power of 4, 4 to the 1 is 4, 4 squared is 16, 4 cubed is 64, 4 to the 4 then is 256, 4 to the 5 is going to be 1024, and 4 to the 6 is going to be 4096. So in this case, we actually do have 2 different options for 4-digit powers of 4 here, so we couldn't have started with this clue, but now we know the last digit is a 6, we get 4096 here, and the question says 8 of the digits from 0 to 9 are used in this cross number. What's the sum of the ones that are not used? Well, we can see 1, 2, 3, 4, 5, 6, 9 and 0 are all used here, so the ones that are not used are 7 and 8, and so the answer to this question is 7 plus 8, which is 15, and so the answer is D. Jill was given a large jar of jam, and she gives 1/6 of the jam to Jan. So once she's done that, she will have 5/6 of the jam left for herself. So let's say that she starts with x, then at this point she'll have 5/6 of x left. Now Jill gives 1/13 of the remaining jam to Jazz. So of that remaining jam, Jill will retain 12/13. So she will at this point have 12/13 of 5/6, or 12/13 multiplied by 5/6 of x. We can simplify down that fraction. We can see there's a factor of 6 top and bottom here, so I'm just left with 10/13 of x. and we know that that is exactly 1 kilogram of jam. So 10/13 of x is equal to 1, and that means that x is equal to 13 over 10. Either do that in one step or two. You could multiply by 13 and divide by 10 if you want to, but it means that the amount she starts with is 13 over 10, which is 1.3 kilograms, and so the answer here is B. So we've got a square, an equilateral triangle, and a regular pentagon, and we want to work out the size of angle WTS. So the first thing we need to do is to actually mark on WTS here, because it's not labelled for us. So WTS would be this angle here. So we'll start with the things we know. So we know in an equilateral triangle the angles are all 60 degrees, and we know of course in a square they are all 90 degrees, the interior angle, and in the pentagon perhaps you know that the interior angles are 108 degrees as well. But if you didn't, you could use the formula to work it out. I think sometimes the easiest way to do it is just to work out the exterior angle first, because that's the easiest formula. It's just 360 over n, so 360 over 5 here gives you 72, and then 180 minus 72 gives you the interior angle of 108. So however you want to get there is fine, but that gives us a way into this triangle TSW, because I can now work out this angle in here. That's 360 minus 90 minus 60 minus 108, and if you work that out, that gives you 102. So this angle here is 102, and now we know this triangle STW is isosceles, and this is really key to solving this problem. And the reason it's isosceles is because this is an equilateral triangle, so all of these side lengths are equal. But now this side length is in common between the equilateral triangle and the square, so this side length is also the same as all of these, but then this side length is in common with the pentagon, so that one is equal to all of these, and then we see that these two really are equal, and so we've got an isosceles triangle. So if this angle here is x, then this one is also x, and that's what we want. So we want 2x plus 102 is 180. So we'll have that 2 times x is 78, and the angle that we're looking for is 78 divided by 2, which is 39 degrees, and so the answer here is E. Problems about the mean are often solved by using the sum of the numbers involved. So if you have the mean, that's the sum of the numbers. You add up all the numbers and then you divide it by n, which is how many numbers there are, and so the sum of the numbers is always the mean multiplied by how many numbers there are. Here we've got the mean of p and q is 13, so there are just two numbers, so that means that p plus q, the sum of p and q, is 13 times 2, which is 26. Similarly, the mean of q and r is 16, so I've got that q plus r is equal to 2 times 16, which is 32, and the mean of r and p is 7, so I must have that r plus p is 7 times 2, which is 14. There's a bit of a trick here that comes up a lot, which is that if we add up all of these equations, we've got this nice symmetry where you see we've got all the different possible pairs. If you add them all up, you get 2 lots of p plus 2 lots of q plus 2 lots of r, right? If I combine all of the left-hand sides. So in total, that must be the same as the sum of all of the right-hand sides here, 26 plus 32 plus 14. So if you add those together, that's 58, 68, 72. Now if I divide both sides by 2, I get p plus q plus r is equal to 36. And now the mean of p, q and r is just the sum of those numbers, p plus q plus r, divided by 3. So I just want to divide that by 3, and we get that the mean of those numbers must be 12. And so the answer is A. Clearly for this question we need to draw a diagram. We've got a regular octagon, P, Q, R, S, T, U, V, W, and it's got side lengths of 2 centimeters. And you've got to always label either clockwise or anti-clockwise, it doesn't matter, but you must keep those letters in the order they are in the question here, and it's important here because I'm going to shade in rectangles PQTU and RSVW, right? So I've got that order right. So PQTU is going to be a rectangle here, and then RSVW is going to be a rectangle here. I'm not going to actually shade them in, but it says 4 small triangles inside the octagon would remain unshaded. So that's this one here, this one here, this one here, and this one here. Okay, and what's the total area in centimeters of these? In centimeters squared of these 4 triangles. And the easiest way to see this would be to say, well, look, I know this is 2 centimeters, and you can kind of imagine just putting those 4 triangles together, right? So actually, if I move this one into here, right, and then I could do the same up here, and then I can move this one into here, I'm going to end up exactly with a square, and that square has side length 2 centimeters because it's the side length of the octagon, so the area is 2 times 2, which is 4. If you wanted to do it a different way, and some people would probably start doing this if you didn't spot that, you could say also, well, this is a right-angled triangle here. Perhaps you might want to think about the interior angles of the octagon being 135 and this being a right angle, and so this being 45 to really be sure. But you could also then say, well, if this side length of the triangle is x, then by Pythagoras' theorem we know that x squared plus x squared is going to be 2 squared, or 4, right? So we've got 2x squared equals 2, and so 2x squared is going to be equal to 4, x squared is equal to 2. So x here is going to be the square root of 2. Now, the area of this triangle, half base times height, is then a half of x squared, so that's going to be 1, and then if I add 4 of those together, then I'm going to get back to the same answer where the area is equal to 4. But that's a much more long-winded way of doing it, but sometimes you might notice doing in a real maths challenge, if you do it that way, you get the answer, that's fine. Of course, we're trying to look out for these slicker ways of doing it where possible, but really we don't have time in the real challenge to think about all of these different options. But hopefully seeing them in this course will help you spot them more often. Which of these are possible polygons? So a triangle with all 3 sides the same length but 3 different interior angles. Well, if you've got a triangle where all 3 sides are the same length, then it is necessarily an equilateral triangle. And we know that in equilateral triangles, all of the angles are 60 degrees, so certainly that is not possible. Similarly, if you have a quadrilateral with all 4 sides the same length, it might not be a square necessarily, but it will at least have to be a rhombus, and in a rhombus the opposite angles here are going to be equal, so we can't have all 4 of the angles being different. The last one is a bit harder to think about, the pentagon. Can we have 5 sides the same length and 5 different interior angles? You can start playing around with this and looking for examples, but one way to get one here that works is to take that equilateral triangle and attach it to the rhombus that we've just thought about here. So I could make all of the side lengths the same here, and this equilateral triangle will have a 60-degree angle, and as long as I don't make this one down here 60, so let's say I make this one something like 50, then this one will also be 50, and this one would be 130, and this one would be 130. So actually, when I remove this line here and combine these angles, right, I've got 130 plus 60 here, which is 190, and then I've got 50 plus 60 here, which will be 110, and now I have got a pentagon here where all the side lengths are equal, but the angles are all different. So it is possible to do that one, and so the answer here is that the only one that's possible is the pentagon, and so the answer here is A. Okay, so let's draw a right angle triangle and call the side lengths A, B and C as we usually do. We're told here that the sum of the side lengths A plus B plus C, that's equal to 16, and that the sums of the squares of the side lengths A squared plus B squared plus C squared is equal to 98. Now as soon as we see sums of squares, we have Pythagoras' theorem in mind that tells us that A squared plus B squared equals C squared. Okay, so we actually could replace the A squared plus B squared in this equation with another C squared, and then we would get that 2C squared is equal to 98, and so that gives us C squared equals 49, which of course means that C is equal to 7. So I could go back then at that point to these equations that we started with and just replace C with 7. So I'd have in the first one A plus B is 16 minus 7, which is 9, and then I've got here just A squared plus B squared is equal to 49. Now we are still quite away from the solution here, because now I have got to work out the area, right? I want to work out the half times the base times the height, so a half AB here. So we've got simultaneous equations for A and B, one linear, one quadratic, and if you've done enough maths, you'll know that you would be able to solve those by substituting one into the other and doing some rearrangement. That's not necessarily going to lead to a very nice answer here, and it's going to be quite a lot of work for a maths challenge question. Okay, we're at question 16, so things are getting harder, but they don't usually require you to do lots of really complicated algebra like that. It's not the It's perhaps a bit of an unfair question because you don't know at this point really whether it will work out nicely. Often you're used to things factorising when you do this, so you might expect that the quadratic's just going to work out nicely. But what you really want to do here is to think outside the box a little bit and to try and do something different. So there's a really, and this trick actually comes up surprisingly often. So one thing you can do here is to say, well, I know I want half AB, so what if I could get that without actually working out A and B? And the way to do it here would be to do A plus B all squared, right? And if you multiply that out, you know you've got A squared plus B squared plus 2AB. Now, but look at what we've got. We've got A plus B is 9, so this is 9 squared, and we've got A squared plus B squared is 49. So actually, I know that 9 squared equals 49 plus 2AB, so 2AB is 9 squared, which is 81, minus 49. 81 minus 49 is 32. So that would give us that AB equals 16, and a half AB, which is the area of the triangle that we're looking for, would be 8. And so the answer there is A, without having to go through that complicated simultaneous equation route. So I think a very tough question there, but a really nice one if you've thought about this sort of thing before. It's a topic you might do quite a lot more if you do A-level further maths. But being really familiar with some of these factorizations, you know, that A plus B squared is A squared plus B squared plus 2AB, that A minus B squared is A squared plus B squared minus 2AB, and of course the famous difference of two squares result that A squared minus B squared is A plus B times A minus B, all really, really useful for maths challenges. So we want to find the ratio of the perimeter of this rectangle to this unfolded rhombus. Well, the perimeter of the rectangle is easy. It's just 3 plus 3 plus 2 plus 2, which is 10 then. For the rhombus, we notice that for each of the four triangles here, the height is 2 and the base here is 1.5. So you could use Pythagoras' theorem to work out the hypotenuse, but it's faster if you can spot that they're in the ratio 3 to 4, because that means that this is a 3, 4, 5 triangle. We've got that famous Pythagorean triple that we use all the time, that's 3 squared plus 4 squared equals 5 squared, and you can always scale that up by any scale factor you want. So here it's exactly half of that. 1.5 is half of 3, 2 is half of 4, so the hypotenuse here is going to be a half of 5, which gives us 2.5. So actually the perimeter of the rhombus here is 4 times 2.5, which is 10. So actually both perimeters are 10, they are equal, and so the ratio is 1 to 1, and the answer is C. I think if you started just listing out primes and square numbers here, you'd probably get the right answer. But because it's not going to be E, you won't be absolutely sure that there aren't any others that you haven't found. Now, how many squares are 4 greater than a prime? I see in here immediately alarm bells of difference of 2 squares going off, right? Because I've got this prime number P is going to be n squared minus 4, where n is a whole number, so I've got a difference of 2 squares that I can use here, and I can write P equals n plus 2 times n minus 2. For something to be prime, its only factors can be 1 and itself, so if I can write P as a product of two numbers here, then one of those numbers has to be a 1. So I can take n minus 2 equals 1 to give n equals 3, and n plus 2 equals 5, and that's going to be the only option, because I can't take n plus 2 to be 1, or n would be negative, and that won't make sense in this question. So there's only one option, it's where n is 3, so that would be the square number being 9 and the prime number being 5. We're going to do this question first on easy mode. What do I mean by that? Well, often in algebra questions, sometimes in other questions, because there's no option here that says it depends on the value of n, we know the answer to this question is going to not depend on the value of n, and there is always going to be an answer because it's a well set question. So what I need to do is to take a value of n here that makes all of the possible answers different. So the simplest one I think would be to, well, let's take 3, because I've got 1 and 2 here. This option would be 3, this would be 5, and this would be 8 then. And if I just work out 3 over 4 minus 5 sixths, then I will get 3 over, 4 is 24 sixths, so 24 sixths minus 5 sixths will be 19 sixths. So that's 3 times 6 19ths, that's 18 19ths, and the difference between the numerator and the denominator then is 1, and the answer must be E, 1. Of course, if you wanted a full written solution, wanted to write this up for an Olympiad or something, or just wanted to do the question fully, you would have to do the algebra. So let's do that as well, just to be clear here. So it's n over n plus 3 times n plus 1 minus m plus 2 all over m plus 3. So you've got to be good with the algebraic fractions here. Now I want to make sure this top fraction is definitely the main fraction here still. So if I divide by a fraction, right, I've effectively got n divided by all of this, then it's the same as turning the fraction upside down and multiplying. So actually I could just write n times m plus 3 here and get rid of the m plus 3 from the bottom. Now the top is factorized, we'll leave that as it is, and we'll just multiply out the bottom here. I get n squared plus 4n plus 3 minus n minus 2, so that gives me n times m plus 3 over n squared plus 3n plus 1, and actually multiplying out the top here, that's n squared plus 3n over n squared plus 3n plus 1. There's no way of simplifying that, and we see again there's a difference of 1 here between the numerator and the denominator, and so the answer is E, but I really think easy mode is the way to go for this question. You know, we want to do things properly mathematically, but part of the maths challenge is, part of the challenge, I mean, is doing it in the time. So if you can find a fast way to get the answer, this is actually a kind of expert level way of doing it. It's not a cheat at all. A lot of people find these sorts of questions very confusing, and probability, as soon as we get into conditional probabilities, can be a bit counterintuitive. What we want to do here is to draw out a sample space diagram. So I've got all of the possibilities, right? I've got the first die on the top and the second dice on the down here. So for example, you know, this corresponds to getting a 2 on both dice, whereas this square here would correspond to getting a 4 on one and a 5 on another. There's a corresponding square where you get a 5 on one and 4 on the other one. Hopefully you've seen that sort of thing before. Right, so given that we know at least one of the scores obtained is a 3, that narrows us down to being in one of these cells here, all of which are equally likely. So all of these cells have 1/36 probability of occurring, because there's 36 in total. But given we've got a 3, there are only these 11 options here. So the probability of getting 2 3s is, given that I know that I've got at least 1 3, is just this cell here, 1 chance out of the total of 11. So the probability here is 1/11. Now, there are some really famous probability problems that are like this, and I would say if you want to think a lot more deeply about this, I've got a video that I've put on YouTube that I'll try to remember to link below, but if not, it's just called the Tuesday boy problem. And there's a famous problem called the 2 boys problem that says, you know, given you've got 2 children and one of them is a boy, or I should say someone tells you they've got 2 children and one of them's a boy, what's the probability they're both boys? And there's lots of interesting arguments you can make about how that question is phrased, and what the answers are to problems like that. So you introduce this extra information about the boy being born on a Tuesday, and it changes the whole setup. So have a look at that video if you want to think more deeply about this, but for here I will just leave it at that. This question has 3 shapes. I've got the semicircle that is this way up, that's this one here. I've got the semicircle that is this way up, that's this one here. And I've got the right angle triangle. And if we combine those 3 in a clever way, we can make this question relatively easy. So this first semicircle has radius 3, this one has radius 4. So we just need to think about combining these. So the first semicircle would have these 3 parts of the diagram. If I add that to the second semicircle, then I'd be shading this part, and this part. And if I subtract off the area of the right angle triangle, then that would have that would mean I'd subtract this part, and this part, and I would be left exactly with the 3 sections that we're looking for here. So all we need to do is work out the areas of these then. So the first semicircle is going to be half pi r squared with r equals 3, so that's a half pi times 9, so let's write that as 9 over 2 pi. The second semicircle, a half pi r squared with r equals 4, so that's a half of 16 pi, or 8 pi. And then for the right angle triangle, I need to do half base times height, so that'll be a half times 8 times 6, because the radius of this circle is exactly half of the base here, and the radius of this one is exactly half of the height. So putting those together then, we've got 9 over 2 pi plus 16 over 2 pi, and then this is 4 times 6, which is 24, so we have 25 over 2 pi minus 24, and so the answer here is A. Standard simultaneous equations methods here would lead to some quite nasty algebra, but we do notice that there are some nice things in these equations. We've got symmetry in the sense that there's 23 and 977 in both equations here, and also in the numbers 2023 and 2977, and those two numbers, 23 and 977, add together to give 1000, and that's going to be quite helpful. So let's call the first equation A and the second equation B, and if I add those two equations together, what we would get then is 23x plus 977x, that would be 1000x, and 977x plus 977y plus 23y would be 1000y, and adding 2023 to 2977 would give us 5000. So dividing this equation through by 1000 gives me x plus y equals 5. At this point you could take that and substitute back into one of the equations and work out x and y. It wouldn't be so bad, but we're still in a maths challenge, so we're still on the lookout for some nicer ways of doing things. So let's take the first equation away from the second equation. Then we'd have 977x minus 23x, and that would give us 954x, and we would have 23y minus 977y, so that's minus 954y. And then we've also got 2977 minus 2023, and that will give us 954. So if I divide this equation through by 954, we get that x minus y is equal to 1. Again, you could at this point solve for x and y. It wouldn't be too hard here. We've got two easy simultaneous equations now. But we notice we only want to work out x squared minus y squared, so we've got an opportunity to save ourselves even more time here and say that using the difference of two squares, we've got x squared minus y squared is x plus y times x minus y. Well, we've just worked out x plus y and x minus y, so here that would be 5 times 1, and that would give us 5, and so the answer here is E. This question we want to be able to multiply 6 numbers together from 1 to 9, different numbers, to make a square number. We're told there are two different ways of doing it. So let's just start by thinking about those numbers from 1 to 9, and questions like this are always going to be about prime factorizations. So 1 is just 1, 2, 3, 5 and 7 are all prime, but 4 is 2 times 2, 6 is 2 times 3, 8 is 2 times 2 times 2, and 9 is 3 times 3. Now if I'm going to multiply a collection of these numbers together and get a square number, I need to make sure that the final result just has even numbers in the power, right? So what I mean by that is that if I have a square number, let's say I take x equals 2 times 3 squared times 5 to the 4 times 7, when I square x, I suddenly get even numbers in the power, right? So I get 2 squared times 3 to the 4 times 5 to the 8 times 7 squared, which is this number multiplied by itself. So I've got to be able to take 6 of these numbers in the list and multiply them together so that there's only even powers. Now 5 only appears once, so I could never use 5 as part of this answer because I would need to have 5 times 5 in there, not just 5, or 5 to the power of 4. So I've got to rule that one out. 7 as well has nothing else that I can pair it with, whereas everything else is just made up of 2s and 3s, so I've got a bit more of a chance. So next what I'm going to do is just think about what happens when I multiply together all of these numbers. 1 times 2 times 3 times 4 times 6 times 8 times 9. Because this is a list of 7 numbers, so to get a list of 6 numbers I'm just going to exclude one of these numbers and see if I can get a square number. So how many powers of 2 are there? Well, there's 1, 2, 3, 4, 5, 6, 7 in total. So it's 2 to the power of 7, and then there's 1, 2, 3, 4 powers of 3. So actually, this is fine for a square number, but this 7 would need to be an even number to make it a square number. So when I think, what numbers can I exclude to make this a square number, and I'm only allowed to exclude one number from the list to be left with 6 others, well, I'm not going to exclude the 1, obviously. If I excluded the 2 and did 1 times 3 times 4 times 6 times 8 times 9, that would give me 2 to the 6 times 3 to the 4, so that would work. I could also exclude the 8 and do 1 times 2 times 3 times 4 times 6 times 9. That would reduce the power here by 3, so that would be 2 to the 4 times 3 to the 4. So they are actually the two ways that will make this work. And you can't exclude anything else, right? Excluding 6 would make 3 an odd power now. excluding 9 would keep the 3 as an even power, but the 2 would still be an odd power, so it wouldn't work. So let's say that this one is our p squared and this one is our q squared. Then to work out the value of p, I need to do the square root of 2 to the 6 times 3 to the 4. Well, by the work we did at the start to show square numbers have even powers, the square root of this is just half of you just need to half each of the powers, right? So I'd get 2 to the 3 times 3 squared. So that would be 8 times 9, which is 72. And for q, I want to do the square root of 2 to the 4 times 3 to the 4. So that would be 2 squared times 3 squared. That would be 4 times 9, which is 36. So the answer to this question, the sum of p and q, is 72 plus 36, which is 108. And so the answer here is D. Here we want to know which of these conditions ensures that Vxq is a straight line here, i.e. Qx and V all lie on a straight line. That's going to happen if the gradient from V to x, the slope from V to x, is the same as the slope from x to q, right? In that case, there'll be one single straight line. If the slope's not the same, then it won't be a straight line. So the slope or the gradient of a line is just the change in y divided by the change in x, the rise over the run if you want. So let's think about what that is for the top square here. So we've got c across, and then this distance here will be d minus a. So let's just write that in there. And for the bottom one, well, we know it's a up, that's fine. And then the horizontal distance we're interested in here will be b minus c. So let's write that in there. So for those slopes to be the same, I'm going to need that d minus a over c. That's the rise over run for the first slope. Okay, technically I'm working with a negative the gradient here because it's going down, but the same thing, you can times both sides by -1 and get the same result here. So that's going to be the same as the slope of this line, so that would be a over b minus c. Let's multiply both sides by b minus c and then by c, and we'll get d minus a times b minus c is equal to ac. Multiplying out the left-hand side, we get db minus dc minus ab plus ac equals ac, and then subtracting ac from each side, we're left with db minus dc minus ab equals 0. Now, this is then a condition that would be perfectly good, but we still need to get it into one of these forms, which is one of the challenges of this question. Now you can see all of the forms from A to E here have A, B, C and D appearing exactly once, so that's how I'm guided in the next step here, right? Because like these two expressions have A, B, C and D in them, but DB has something in common with the other two. So what I notice is if I divide everything through by DB, right, so this is then 1, right, I'm going to try and get the 1 from dividing through by something here, but if I divide DC by DB, then the D's cancel. If I divide AB by DB, then the B's cancel, and so I get something like that. But I've still got an A, B, C and D in these expressions, and that's exactly what I want. So if I just add those fractions to the right hand side and swap the sides of the equation here, that's equivalent to A over D plus C over B is equal to 1, and so the answer to this question is C. This question certainly has an easy mode and a hard mode available to us. And easy mode here is, again, where we say there is something in the question that we can simplify and it's not going to change the answer to the question. So in particular here, they tell us that PQ is a tangent to both of the unshaded circles, but they don't really say anything about how big those individual circles can be. So the fact that there's no answer possible that says like it depends means that we could really put that tangent PQ wherever we want to in the circle. And the easiest place to put that would be to make PQ here a diameter of the circle, and then these two smaller circles would be equal to each other, right? And then this would also be a diameter, so this line would have length 6 units as well. So these smaller circles would have radius 1.5 or 3 over 2, and the large circle would have radius 3. And then the answer to this question would, to get these shaded areas, would just be to do the area of the large circle, so pi times 3 squared or 9 pi. And then I would subtract 2 lots of the area of the smaller circles here, and they would have area pi times 1.5 squared, so 3 over 2 squared times pi, which is 9 over 4 pi. So I've got 9 pi minus 9 over 2 pi, and that just gives us 9 over 2 pi, or 9 pi over 2, and that must then be the answer to this question, which is D. If you wanted a slightly fuller answer to this question that doesn't just rely on those answers, if it was an Olympiad question, for example, or you want to just show some working, one thing we could do would be to let the radius of the smaller circle be small r, and the radius of the larger circle be capital R. Now, the solution to this question is going to be the area of the large circle. Now, the large circle is going to have radius small r plus capital R, because these two together form half of the diameter. So the radius of the large circle here would be small r plus capital R. So that would be pi times r plus r squared. Then I'd want to subtract the areas of the smaller circle, so minus pi r squared and pi capital R squared. If I just multiply this out, I get pi times r squared plus capital R squared plus 2rr minus pi r squared minus pi capital R squared. And what I can see then is that the pi r squared cancels out here, and this one cancels out here, because remember these are multiplied by pi outside the brackets. So I'm just left with the answer to this question being 2r capital R pi. So if I can work out r times capital R, we're done. Now you might know from your GCSE or GCSE circle theorems the intersecting chords theorem, which could be very useful here, right? It says when I've got two chords of circles that intersect at a point, the in general, what I have, if I can draw a reasonable circle here, right, is that if this one is x and this is y, this is a, this is b, right? The intersecting chords theorem tells us that x times y equals a times b. So I could use that here because I know that this section here is 2r, and this one is 2 capital R, and this is 3, and this is 3, right? So I've got that 2r times 2 capital R, that's got to be 3 times 3, so I've got 4rr equals 9. So if I want 2rr pi, well, I just divide that by 2 to get 2rr is 9 over 2, and then multiply both sides by pi, and then we get 9 over 2 pi for the same answer, but shown in a bit more generality. I suppose for really full proof, you might want to justify the intersecting chords theorem or something, and there are other ways to do this as well. But either way, easy mode or hard mode are just as good as each other for the maths challenges. In fact, I would recommend using easy mode. I think it's better when you're in the heat of the moment in the maths challenge and you need to get through the questions quickly, and then think about the hard mode answer once you get home. Either way, the answer here is D, 9 pi over 2.